In this video, we're going to talk about the empirical rule and the range rule of thumb. This video goes along with the 3.2 measures of variation guided notes. Make sure you have your notes out so you can follow along. Let's take a look at the empirical rule. As you can see here, we have a normal distribution of data. It is bell-shaped here. And the empirical rule says that for this set of data, 68% of the data will be within one standard deviation of the mean. See, the mean here is at the center of our normal distribution of data. 95% of the data will be within two standard deviations of our mean. So you can see x bar plus s, x bar plus 2s means two standard deviations above the mean. X bar minus 2s over here means two standard deviations below the mean. And remember, for a normal distribution of data, the mean is right in the center. And according to the empirical rule, 99.7% of the data lie within three standard deviations of the mean. Let's use our newfound knowledge of the empirical rule to complete an example. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? So we know that our mean, mu, is 100 for IQ scores, and sigma, the standard deviation, is 15. We want to know what percent of IQ scores fall between 70 and 130. I'm drawing a number line here, and in the middle of the number line, I'm going to put our mean equals 100. That's the middle of our distribution. Now, I'm going to add our mean plus one standard deviation, or 100 plus 15, giving me 115. Next, I'm going to take our mean and I'm going to add two standard deviations. Well, that's our mean is 100 plus 2 times 15. That gives me 130. 130 is one of the numbers that I'm looking for in this problem. Let's go in the other direction. I'm going to take my mean. I'm going to subtract one standard deviation. So that's 100 minus 15, or 85. Now I'm going to take my mean and subtract two standard deviations. That's 100 minus 2 times 15. 100 minus 30 is 70. Well, that's the other number that I'm looking for. I can see that 70 is two standard deviations below the mean, and 130 is two standard deviations above the mean. We can see here on our graph that 95% of the data falls within two standard deviations of the mean. Two standard deviations of the mean below is 70. Two standard deviations above the mean is 30. So we can say that 95% of the data falls between 70 and 130. 95% of the data falls in this green area. From the empirical rule, we know that 95% of sample data lies between two standard deviations of the mean. From this information, we can use something called the range rule of thumb to determine what we consider our significant values are. So, values that lay within two standard deviations of the mean we call not significant. You might also hear them called usual values. Whereas values that are more than two standard deviations below the mean are called significantly low, or you might hear them called unusual. Values that are more than two standard deviations above the mean are called significantly high values. You might also call them unusual or unusually high. So our minimum usual value, to find that, you take your mean and you minus 2 times your standard deviation. So mean minus 2 standard deviation, mu minus 2 sigma. To get your maximum usual value, you're going to take your mean and you're going to add 2 standard deviations. Now, you might encounter a problem where you know your range of data, but you're unable to determine a standard deviation. Using the range rule of thumb estimating a standard deviation, you simply take your range of your data, so that's the max minus the minimum, and you divide by 4. Let's look at some examples. A certain group of test subjects had pulse rates with a mean of 84.1 beats per minute and a standard deviation of 14 beats per minute. Use the range rule of thumb to identify the limits separating the values that are significantly low or significantly high. Is a pulse rate of 92.1 beats per minute significantly low or significantly high? For this problem, let's first write down the information we know. We're using sample data, so I'll use sample notation. X bar, the mean, is 84.1 beats per minute. The standard deviation S is 14 beats per minute. To find out the minimum value for our non-significant values, we're going to take our X bar minus 2S. So 84.1 minus 14 times 2. We get 56.1 beats per minute. Now we have to find our maximum usual value, which would be X bar plus 2S, or 84.1 plus 2 times 14. We get 112.1 beats per minute. Now we can set these up on a number line to give us a visual of what it means. 84.1 is our mean in the middle. If we go up 2 standard deviations, we'll be at 112.1. If we go down 2 standard deviations, we'll be at 56.1. Now, the values that are in the middle between these numbers we consider are not significant values. So the minimum usual value is 56.1 beats per minute. The maximum usual value is 112.1 beats per minute. Anything that is lower than 56.1 or higher than 112.1 is considered a significant value. So we're now asked, is a pulse rate of 92.1 beats per minute significantly low or significantly high? Let's put it on our chart. So I'm here at 84. So 92.1 would be about there on our number line. As you can see, that falls into our yellow area. So it is not significantly high or low. So 92.1 is not significant. Why is it not significant? Because 92.1 is between 56.1 and 112.1. For our final example, we'll use the range rule of thumb to estimate the standard deviation. In a group of 17 students, the maximum height was 75 inches and the minimum height was 58 inches. Use the range rule of thumb to estimate the standard deviation of the heights of students in the group. So taking the important information in the problem, I can say that my maximum is 75. The minimum is 58. To estimate our standard deviation, we take the maximum minus the minimum and divide by 4. So the range of the data divided by 4. And that's 75 minus 58 divided by 4. We get 17 divided by 4, which gives us 4.25. Now, we round out to 1 decimal place further than the original data, so we're going to round that to 4.3 inches. That is our estimate for the standard deviation.